Okay. Hello everybody. I'm Alejandra and I'm the head of sustainability at Flightkeys. It's a pleasure to be here with you all and to tell you what we do, at Flightkeys. I'm going to start introducing the company in case some of you were not familiar with our job. So what is Flightkeys? Flightkeys is a flight planning software company founded in 2015 and based in Vienna. We provide flight planning services to airlines all around the world, mostly in the US, Europe, and Oceania. We have 3 tools: Flightkeys 5D, which is the flight planning tool, Spacekeys for rain prediction, and an EFB tool, Loretta, for pilots to use in flight. So I usually like to start the presentations with a bit of a personal touch. I guess Mark Stettler already went through the science way better than I can, but I wanted to show in like a personal perspective how much contrail avoidance can affect us all. So maybe it's hard to guess from my accent, but I come from Madrid in Spain, where my family is currently living. And as Joachim said, I'm also a PhD candidate at the University Carlos III of Madrid, which means that in order to keep my mother happy and my PhD supervisor happy, I need to return to Spain at least 6 times a year, which is 12 flights go and return. And I mostly take the evening flights because it's just more convenient to go after work. I actually came from Madrid yesterday. I went there to celebrate my dad's birthday. And before going, I checked what the predicted contrail formation would be on the evening of my flight there. So on Thursday, the 20th of March. And the results came out that just from contrail formation alone, there might have been contrails being formed that could have been responsible for 9,000 kilograms of CO2e extra to the already CO2 produced by fuel. This is for one evening flight. You have to multiply that times the 12 flights I go. And this is without counting all of the work flights, private flights, visiting friends, etc. And I guess that looking at all of you here, all international faces in this room, I guess we're all in the same boat. We're all frequent flyers. And it's nice to think that even though we need to fly, we can, learn to do it better, learn to fly better, and maybe help the environment while also being able to come visit my mother at least 6 times a year. So in order to do this, we are collaborating with academic people, big tech people, research organizations, and of course the airlines to bring contrail avoidance from the lab to the operator side. So how does Flightkeys solution work? We have both the pre-tactical and tactical avoidance as like a joint full circle. Raymond is going to do a demonstration on the second day, so I'm not going to go through this very in depth. But the idea is that we import the contrail areas as like a separate weather layer, and then we perform an analysis on all flights to see which of them would be more likely to form contrails. We then select the most warming one and perform a rerouting around the contrail areas. These new flight plans are then filed. If approved by ATC, they get uploaded to our EFB tool in flight, so pilots can check the latest contrail forecast with updated weather data. And last but not least, once the flight has been finished, we do a reanalysis data for both the planned flight plan and, if possible, the flown flight plan to see how effective the reroutings were, and then to go back and improve the contrail forecast models. We published a paper at the beginning of last year where we simulated a big number of American airline flights using polygon-based or hard restrictions as contrail areas. This added a lot of complexity into the airspace, but it proved that despite the complexity, we can achieve a big reduction in energy forcing with small increases in cost, fuel, and time for the airline. These were the results that Mark Stettler was supposed to talk through, but didn't have time. Since then, we have moved to cost-based avoidance. So now instead of polygon-based, that was not going to be feasible from a practical ATM perspective. So now what we do is that we give a perceived cost for energy forcing formed, and then our cost optimizer can account for this cost when doing the optimization. The higher the perceived cost of control formation, the more our optimizer will try to reroute around these areas. And this gives us a wide range of possible rerouting solutions to play with, from 0, so no contrail avoidance, to a cost of 100,000 million, and then the optimizer would reroute around every single contrail area that it can find. Also, last year and this year, we started with some flight trials with some of our customers. TuiFly, we're gonna also now go through some of the results that Christoph mentioned, and American Airlines, and we're doing this in collaboration with Breakthrough Energy and Google. And last but not least, in February of 2025, we began with the A4 Climate, which wants to be able to simulate, to fly at least 400 flights with contrail avoidance routings. So now let's go into the TUI trial results. So as Christoph said, the TUI trial happened in a very intense week. So out of the 312 flights that we were checking between the days of the 17th and the 23rd of February, 203 flights were predicted to form warming contrails. Out of these 103 flights, we were not going to target all of them because we only were looking at the more extreme cases, and also, as he mentioned, not all of them could be rerouted for other reasons. So at the end, we ended up filing 84 flights. And where were the results? Well, the results showed this. Christoph showed the results for the 84 flights in particular. I'm going to show the total increase compared to the cost optimal results for the total 312 set, including the 84 rerouted flights. So the results are quite similar to what we got in the first paper. The increase in cost, fuel, and time are underneath 1% for all cases. The decrease in forecast energy forcing, this is because for our optimizer, we decided to go to the most extreme case possible, so reroute as much as you can around contrail areas. We set up a very high price, so the optimizer planned to reroute at least throughout all warming contrails, and the negative there is because there might have been some cooling contrail that just added it to the warming. Then, after the flights took place, we did a reanalysis data with the Contrail COSEP API, and with this new setup, we would have decreased the contrail energy forcing by 42.86% compared to the cost optimal arrangement at the beginning, and the total warming in CO2e for a time horizon of 100 years' time by 13.42. This also includes the 0.52 increase in fuel. So the extra fuel and the contrail reduction lead to an overall total reduction of the warming of 13.4%. And something that I wanted to check about myself as an own personal experiment, because that's something that gets asked all the time, is what would happen if instead of flying with contrail avoidance, we would fly with minimum fuel. So in our system, every customer can set up different flight plans configuration, and it so happens that TuiFly always chooses to create an extra minimum fuel flight plan, so that made it very easy to check what the minimum fuel flight plan would have been compared to the contrail avoidance flight. From an operational perspective, we see that surprisingly, the contrail flights are actually cheaper to fly than the minimum fuel flights. Well, surprisingly or not so surprisingly. Fuel-wise, fuel-wise, contrails do burn more fuel than the minimum fuel. And time-wise, same thing. I don't know why the sign there got mixed up, but it's negative. This is all compared to the cost-based. So the percentages are all based to the cost-based flight planning versions of these same flight plans. And from a climate perspective, we see that the total warming for the minimum fuel is even a bit higher than the cost optimal, because we're assuming we're producing more contrails in the minimum fuel than we were in the cost optimal. So overall, the total warming in CO2e in a time horizon of 100 years from now would be way less in the contrail avoidance compared to the minimum fuel. So it would have been a no-brainer and definitely a very interesting exercise to see. These are all the preliminary results. We're still doing more analysis on all of these flights, and as Christoph said, there's more trials coming potentially in the summer, and it will be very interesting to see. It was definitely a great experience also to see how the dispatchers and the pilots dealt with all of these reroutings, And I would say that from our side, it has been a very successful trial, and we look forward to keep working with TUI to, well, progress on contrail avoidance. And that's all from our side. If you guys want, again, Raymond will do a presentation, a demo of both the Loretta tool and the Flightkeys 5D tool tomorrow. But if you guys want to see it firsthand, come outside. We have a booth there with the computers, with the iPads, and you can, we can show you personally how airlines use the feature. And yeah, come play around with it. Thank you.
Hello, everyone. I'm Adam Durant, Chief Executive of Satavia, now part of GE Aerospace Carbon Solutions. So Mark gave us a really good explanation of why we're here, why are we doing this. The latest science tells us the problem is as big as CO2 in terms of climate impact. So I'm going to explain how we can do this, at least one way we can do this, within existing flight operations. And so the main principle that Mark also highlighted is that if the cloud doesn't form from the aircraft emissions, then we don't have the heating effect. And so we focus on a practical solution of solving the problem at the pre-tactical stage before the aircraft departs, and targeting warming contrail flights. One of the key principles we've got to prove is the counterfactual, that had we not intervened, then the warming would not have taken place. And that's quite a challenging thing to prove. And importantly, we've also got to come up with ways of trading off other impacts, such as CO2 emissions, other non-CO2 impacts, such as NOx and soot, when we make a decision about deviating a flight. So all of that needs to be factored into any solution that then results in a flight deviation, in order to build confidence that we're actually generating a net improvement in the problem. So I'm going to go into some basic information on trials we ran in 2023 with support of the European Space Agency, and I'll end with some of the learnings from those trials. Quickly to introduce one of our team members, Dr. Greg Thompson. He's sat just over there. He's an expert in numerical weather prediction. He now works full-time at GE Aerospace, on the back of a 30-year career, largely at the National Centre for Atmospheric Research. So Greg's one of the model developers of the WRF model, expert in cloud microphysics. I'm originally an academic. I did graduate school at Michigan Tech in the US, started off in earth science, working on volcanic ash, crossed over into atmospheric physics, did some fundamental research on ice nucleation in the lab with Dr. Raymond Shaw, did postdocs at Bristol University on climate modeling, working on the dust cycle. So that's another interesting problem. Does it create a warming or a cooling effect? Ended up at Cambridge looking at small sensor technology, sensor networks for trace gas measurements, and then ended up entering the world of aviation on the back of the volcanic ash cloud events in 2010. So I worked for a spin-out of the Norwegian Institute for Air Research, collaborated with Airbus and EasyJet for some years before founding Satavia. So Satavia was intended to bring the best available science to solve problems in aviation around predictive maintenance and more recently around climate. I'm going to talk more tomorrow about a lot of what we've done, but just to give you some background of where we are now. So we're part of GE Aerospace. GE Aerospace obviously builds engines, so we've got the engine part of the company. There's also a company called Software as a Service, so they provide various software solutions, work with pilots to help them make better decisions on the flight deck that can save fuel and other things. And more recently, GE Aerospace span out Aerospace Carbon Solutions. So we're now part of that company. ACS does a number of things, looking at compliance preparedness, so budgeting and cost management for airlines. SAF purchasing, so we've got great visibility on supplies globally and pricing, and so we can do forwards projections of those kind of things. Fleet-wide analytics, and more recently now, we bring in the contrails and non-CO2. And so our whole mission really is to help optimize flight operations, and manage the costs of regulatory compliance. And so we've got some interesting new developments in the world of non-CO2. So our technology is based on numerical weather prediction modeling. We started doing this back in 2018 with support from the Aerospace Technology Institute. We were working on a different problem at the time, engine icing. And so we developed the technology really to originally look at how often aircraft will encounter conditions that lead to compressor icing. We worked with Rolls-Royce on that. And then in 2020, when the contrail issue became more widely accepted, we pivoted to looking at how we could then offer the same kind of information within the domain of flight operations to enable airlines to make decisions about how they could reroute to avoid ISSRs and forming warming contrails. It's not just about the weather predictions, it's also understanding if a cloud forms, what will its net relative impact be if that cloud is allowed to disperse in the atmosphere and fully live out its effects on the atmosphere. So we combine both NWP with modeling using COSIP, and so there's various use cases for this, monitoring, reporting, and verification, flight plan optimization, and we're also developing a market-based incentive for operators with Gold Standard, which is a major carbon accreditation platform. Obviously, we're being guided by the science, so being part of GE Aerospace actually has opened up huge opportunity about what we can do. So we bring in the numerical weather prediction. There's various collaborations that we're leveraging, such as with NASA and DLR. We recently did a flight test program called Codex with NASA. I'll talk more about that tomorrow, but this is really where we're helping and contributing to understanding and advancing the core science. And in December of last year, we published our paper looking at the skill of numerical weather prediction models and how well they can do humidity predictions and forecasts. Worth mentioning also the GRC team. So this is the General Electric Research Center team based in Niskayuna, New York. So there's several hundred researchers fully focused on research and technology in this research center. And there's a significant number of them now working on non-CO2. So this is not just looking at things like contrail avoidance, but it's also looking at future engine technologies and understanding all the consequences of future engine design and architectures. And so now we leverage this amazing ecosystem of researchers in everything that we're doing. So the way we see this evolving, obviously there's a strong need to understand the problem coming from the new requirements out of the EU ETS. And so obviously supporting information on climate impact for airlines, and where we want to get to is helping to reduce that. And so we see a sort of timeline of probably less than 5 years where we can make a tangible impact. Our solution is called DecisionX. We're combining that with the ACS signpost solution, but essentially this is going to combine both the MRV accounting and also the flight plan optimization in a single solution, a module within capability that also looks at decarbonization and off-the-engine decarbonization technologies. So I'll just talk some of the history. So we started this in 2021 with Etihad. So I actually went out, fully immersed myself in the flight operations department. This, I spent time walking around the flight dispatch office. In GE, they call this Gemba walk. So this is actually getting to know what's going on locally. So I learned a lot about the flight planning process, the roles of different personas within the organization, and it became apparent that we could do something today with an existing flight planning process. I also got to know the pilot. So that's Captain Mimo Catiano. He was the Boeing 787 type pilot in Etihad, and he got personally involved throughout the trials. And that we found was a key enabler to the success, because not only did he help the pilot community understand what we were trying to achieve and the source of the problem, but just as we saw in the earlier presentation, quite often pilots don't necessarily follow the flight plan. They're getting information from the FMS that tells them to do something different. So just a fundamental understanding of the problem and the benefits of taking action means that our overall success could be improved. So we had good engagement from the flight dispatchers and the pilots. And from that, we were able to develop a very simple, largely manual process for how can we integrate into the existing flight planning process and deliver optimized flight plans that avoid forming contrails. So at the time, our first step was to understand for the following 24-hour periods, what is the airline planning to do in terms of their flight schedule? So the first step was analyzing the flight schedule, making predictions about which flights on a given day would produce long-lived warming contrails. We initially tried to do that 48 hours in advance, but we discovered through doing this that the weather forecasts weren't good enough to make those kind of long-term predictions. So then we moved to doing it all on the same day with a 24-hour forecast. And our paper that was published in December shows the statistics of model skill for a 24-hour forecast. I'm going to keep going. I've only got another 10 slides, don't worry. And so then we developed this process where we worked with dispatchers to take their flight plans, analyze them, give them a briefing pack back that enabled them to manually make changes only in flight levels whilst retaining waypoints. We didn't need to change every single waypoint on a planned flight level. We could change maybe 2 or 3 planned flight levels along a flight plan. And then that gave us a clear counterfactual. What would have happened had they just flown the performance-based flight plan, and then what actually happened when we looked at the ADS-B trajectory. And so that's the final step. A day or so later, we're able to go back and actually analyze what happened retrospectively and do those calculations of avoided impact. And so what it essentially involves doing is a COSIP calculation along the original flight plan, and then a COSIP calculation along the ADS-B trajectory. We can do this both with forecast data or hindcast data if available, and then we look at the total impact for those 2 cases, convert to a CO2 equivalent, and look at the difference. And that's what we define as the avoided impact. We first did this in October 2021 with a flight from London to Abu Dhabi. And so doing that calculation by making a small change that cost us 181 kilograms of fuel to fly at a slightly higher flight level, we were able to avoid over 60 tons of CO2 equivalent impact. This led us to work in 2023 with 12 airlines over 10 months. We analyzed nearly 450 flights. We modified 65 of those. And we had an average saving per flight of around 44 tons of CO2 equivalent impact. So here's the KPIs. I'll talk more about this tomorrow. We can analyze the savings in terms of short, medium, and long-haul flights. We had a slightly better success rate with the long-haul flights. You can see there's an average CO2e saving on the right there by month, by aircraft type. We're going to look at this again in more detail tomorrow, but I'll just end with this final analysis, which really shows us when we looked at all the reasons why we weren't successful, these are the reasons here. Was it an air traffic control restriction? That's in blue. The big red part of the reasons why we weren't successful is it just wasn't, our suggestions weren't implemented by dispatch. So that could be a number of reasons, but automation and software integration can solve a lot of that problem. The green is unable to modify around contrail, so maybe there were some restrictions on airspace that prevented us from doing that. We have a fairly large purple band there. That was French air traffic control strikes that impacted our trial days. A small blue segment there, well, the modification was not flown, so our suggestions were ignored, and therefore the contrails formed and created a negative impact. Aircraft performance is in dark purple towards the top there, so it's a very small segment. But I guess, significantly here, errors in model accuracy, which is brown just below count, is actually a very small part of the reasons why we weren't successful. The biggest challenge right now is going to be around human process and modifying existing processes with air traffic management and flight planning to accommodate contrail management. So this really lends support to we should be doing trials today because the kind of problems we've got to solve first are going to be more in flight operations and air traffic management. And we're going to improve the science over time, but it's going to probably take that amount of time to solve human factors and other things. So I'll stop there. Sorry for going over. Thanks very much.
Thank you, Adam. Thank you so much.